and today I'm going to talk about our work on deep reinforcement learning at the edge of the statistical precipice. This work is accepted at NeurIPS 2021 as an oral presentation. For more details, refer to agarwal.github.io/reliable. TLDR, our findings in this work call for a change in how we evaluate performance in reinforcement learning and machine learning benchmarks, for which we present more reliable protocols, easily applicable with even a handful of runs to prevent unreliable results from stagnating the field. It only requires a few extra lines of code for reliable evaluation. Please see github.com/google-research/reliable for more info. Let's now go to the main presentation. Research in deep reinforcement learning predominantly relies on evaluating performance on a diverse suite of tasks, such as Atari 2600 video games, to assess progress. Quantitative evaluation on a suite of tasks reveals strengths and limitations of methods, while simultaneously guiding researchers towards methods with promising results. Most published results on deep reinforcement learning benchmarks compare point estimates of aggregate performance, such as mean and median scores across tasks. For example, even some of our own prior publications only reported point estimates for showing improvements. Unfortunately, reporting only point estimates ignores the statistical uncertainty implied by the use of a finite number of training runs. Furthermore, beginning with the arcade learning environment, the shift towards computationally demanding benchmarks has led to the practice of evaluating only a handful of runs per task, exacerbating the statistical uncertainty in point estimates. As we move towards more challenging reinforcement learning benchmarks, evaluating more than a handful of tasks will become increasingly demanding due to the increased amount of compute and data needed to tackle such tasks. So, what could go wrong with ignoring statistical uncertainty? To illustrate the pitfalls arising from the naive use of point estimates in the Furon regime, we do a case study on the Atari 100K benchmark. This benchmark contains Atari 26 Atari games, and algorithms are evaluated after 100K training steps, or roughly 2 to 3 hours of gameplay. Prior work on this benchmark typically report median human normalized scores, which correspond to the sample median over the task means, and typically use 3 or 5 runs for computing the median scores. In our experimental setup, we evaluate 100 independent runs for 5 algorithms, namely DER, OTR, TRQ, curl, and SPR. We chose these algorithms as their representative of this benchmark. The score for a given run is the average returns obtained in 100 evaluation episodes taking place after training for a given game. So we have a total of 26 games and 100 scores per game. We then subsample these scores from these 100 independent runs to investigate the statistical variations in the Furon regime. Our first observation is that sample medians reported in the literature exhibit substantial variability when viewed as random quantities that depend on a small number of runs. The reported point estimates of median in publications, as shown by the dashed lines, do not provide any information about the variability in median scores and severely overestimate or underestimate the expected median. This shows that there is a fairly large potential for drawing erroneous conclusions based on point estimates alone. Additionally, the median of sample means is a biased estimate of median of true task mean scores. In the Furon regime, we find that this bias can dominate the comparison between algorithms. So while claiming improvements with 3 or fewer runs may naturally raise eyebrows, folk wisdom in deep reinforcement learning suggests that 20 or 30 runs are enough. By calculating 95% confidence intervals on sample medians, we find that this number is actually closer to 50 to 100 runs in Atari 100K. Far too many to be computationally feasible for most research projects. Additionally, we also comment on the incompatibility of alternative evaluation protocols involving maximum cross runs or during training to end performance results. On Atari 100K, we find that the two protocols produce substantially different results of a magnitude greater than the actual difference in score. So, how do we reliably evaluate performance? We argue that just fixing random seeds is not a solution for the simple reason that why we should prefer one set of seats over another. Also, it is not easy to fix randomness in practice. For example, if we use a different set of hardware, or because of the non-determinism in GPUs, as well as machine learning frameworks such as TensorFlow or JAX. Similarly, evaluating more than a few runs is typically infeasible for computationally demanding deep reinforcement learning projects. For example, 5 runs on 50 Atari games for 200 million frames takes 1,000 plus GPU days. Furthermore, we avoid statistical significance tests because of their dichotomous nature, that is, significant versus not significant, and common misinterpretations, such as lack of statistically significant results does not demonstrate the absence of any improvement. And given enough data, any trivial improvement can be statistically significant, but may not be practically significant. Instead, we emphasize using statistical thinking. Any performance estimate based on a finite number of runs is a random variable and should be treated as such. In this work, we provide 3 tools for reliable evaluation aligned with the principle of reporting statistical uncertainty in results. Let's walk through these tools one by one. The first tool is using interval estimates. Instead of point estimates, which hinder results reproducibility, we recommend reporting interval estimates via stratified bootstrap confidence intervals. These confidence intervals answers the question, if we repeat the experiment with different runs or random seeds, what aggregate score are we expected to get? For stratified bootstrapping, we resample runs with replacement independently for each of the tasks. One thing I like to point out is that with n runs per task on each of the m tasks, we have n times m random samples. For example, on Atari 100K, we have 26 tasks, and if we use 5 runs, we still have a total of 130 random samples. Statistical bootstrapping seems to work well in this scenario, providing reasonably accurate interval estimates. Now, most deep reinforcement learning benchmarks yield scores that vary widely between the individual runs and tasks. Aggregate metrics such as mean and median paint an incomplete picture as they conceal this variability in performance. For example, if you look at the plots in the figure, they have all the same aggregate statistics, but the variability across different points is very different on each of these plots. So while tables with task mean scores can reveal this variability, tables are typically overwhelming for comparing algorithms beyond a small number of tasks. Furthermore, standard deviations are frequently omitted from such tables due to space constraints, and mean scores actually present an incomplete picture for multi-model and heavy-tailed distributions. Instead of tables with per task mean scores, we recommend performance profiles with stratified bootstrap confidence bands. Performance profiles are typically used for comparing solve times of different optimization methods and are robust to outlier runs and tasks. Here we show the performance profiles on the Atari 100K benchmark. These profiles show tail distribution of scores on runs combined across all the tasks. Such profiles allow for qualitative comparisons at a glance. For example, one curve above another corresponds to stochastic dominance. We can also read any score percentile from such profiles. For example, the point where the curves intersect y equal to 0.5, it corresponds to the median. Also, for a positively valued random variable, the area under the profile corresponds to the mean performance. Now, while performance profiles are a great tool for qualitative comparisons, they often intersect at multiple points, as most algorithms do not strictly dominate other algorithms. Thus, finer quantitative comparisons still require aggregate metrics. However, existing metrics are deficient. Mean is prone to outliers, while median is unaffected by 0 scores on nearly half of the tasks and is statistically inefficient. Instead, we need better metrics which are not unduly affected by outliers, have small uncertainty even with a handful of runs, and are more robust indicators of performance. In this work, we recommend alternative metrics based on robust statistics, including interquartile mean or IQM and optimality gap. IQM corresponds to the mean score of the middle 50% of the runs combined across all the tasks and is a better indicator of overall performance than median. Optimality gap measures how far an algorithm is from the optimum performance and corresponds to clipped mean. Both optimality gap and interquartile mean can be read as areas under the performance profiles we suggested earlier. Now, compared to mean, interquartile mean is more robust to outliers. Compared to median, it is a better indicator of overall performance and results in smaller CIs and require fewer runs to claim improvements. It is also much less biased than median. Another metric we propose is probability of improvement averaged across all the tasks. This metric answers how likely the improvement over baseline is, irrespective of its size. This metric is quite useful for head-to-head comparisons. Using our recommended tools for reliable evaluation, we scrutinize performance evaluations of existing algorithms on other widely used deep reinforcement learning benchmarks, including the arcade learning environment, ProcGen, and the DeepMind control suite, again revealing discrepancies in prior comparisons. First, we note that on the ALE benchmark, interval estimates of median scores result in large confidence intervals compared to IQM. And these interval estimates strikingly overlap for certain methods, such as DQ and ADAM and C51. Furthermore, depending on the choice of the metric, the ordering between algorithms changes. This inconsistency in ranking arises from the fact that such metrics only capture a specific aspect of overall performance across tasks and runs. Since performance profiles capture the full picture, they would often illustrate why such inconsistencies exist, and we should always be reporting these profiles. On DeepMind controlled suite, there are huge overlaps in the 95% confidence intervals of mean normalized scores for most of these algorithms. These findings suggest that a lot of the reported improvements could be spurious, resulting from just randomness in the experimental protocol on this benchmark. And on the ProcGen benchmark, we compute the probability of improvement to understand how likely are the reported improvements. In the figure, the algorithm shown on the left claimed improvements over the algorithm shown on the right. However, we find that some of these claimed improvements are only 50 to 70% likely. So what are the key takeaways from this work? We recommend using interval estimates as opposed to point estimates for reliable benchmarking. For qualitative comparisons, we propose performance profiles. Moreover, we argue that when using only a handful of runs, we should consider better aggregate performance measures such as interquartile mean and probability of improvement, as well as report their corresponding interval estimates. We also urge the authors to provide individual runs for better statistical comparisons. To support reliable evaluation in reinforcement learning research and more generally machine learning research, we have released an easy-to-use Python library along with the Colab. See the linked Colab notebook for a quick jumpstart. To conclude, given the substantial influence of statistical considerations in experiments involving 40-year-old Atari 2600 video games and low degree of freedom robotic simulations, we argue that it is unlikely that an increase in available computation will resolve the problem for the future generation of reinforcement learning benchmarks. Instead, just as a well-prepared rock climber can skirt the edge of the steepest precipices, it seems likely that the ongoing process in reinforcement learning requires greater experimental discipline. Thank you. See agarwal.github.io/reliable for more details.